Hi, in this video you'll learn how to derive and understand the kinematic equations. But before that, let's review the kinematic graphs. First of all, xt graph, you need to know the slope is velocity and y-intercept is the initial position. For vt graph, you need to know the slope is acceleration. Y data point determines whether you're speeding up or slowing down. If you're closer to the x-axis, that means you're slowing down. And if you're further from the y data point, it's going further from the x-axis, then it's speeding up. The area under the VT graph is displacement, and the quadrants determine the direction. For AT graph, you need to know the area is changing velocity, and the quadrants determine direction. Okay, let's dive in and learn the first kinematic equation. First of all, we know that the average velocity is the displacement over time, and the average acceleration is changing velocity over changing time. If we grab the second equation here, we can rearrange it into the acceleration equals to v final minus v initial, because the changing velocity is final minus initial, and final times minus initial time. So again, this part represents a time interval that's specific to the period of time that you're considering in a specific scenario. So we would just write it as time. Okay, and now if we multiply both sides by t, we get at equals to v final minus v initial. Conventionally in physics, Vf is represented by just v, and the initial velocity is represented by v0. As a result, by the way, it's in kinematics, so at would equal to v minus the initial velocity. And if we add both sides by v0, we get our first equation, v equals to v0 plus at. Here, the first equation. All right, let's continue and learn the second equation, which is a bit more complicated because we need to connect it to the kinematic graph. First of all, we know that VT graph, the area under the VT graph is a displacement, right? We can see it here. So let's draw a VT graph first. Let's say the curve looks like this. And by the way, the area is this part. So we can write the displacement what equals to the area. When we are calculating the area, we can separate it into two parts. The first part here is a triangle, and the second part here is a rectangle. So we can write the changing position equals to 1 plus 2. We know the area of the triangle is 1/2 base times height. What's the base here? The base is just time, this part, right? So 1/2 times base is just the time. What's the height though? We know this, which is a y-intercept, is the initial velocity on the VT graph, right? Y-intercept is the initial velocity. And what is this part? This is the final velocity, right? So what is the height? It's just final minus initial, which is the changing velocity. And what is the rectangle? I bet you know what's the equation for the area of the rectangle. So it's just V0 times T, right? So let's rearrange and write it again. Okay, so we get this weird expression, but to get our second kinematic equation, we need to connect it to our first equation. Here, we can rearrange the first equation by subtracting initial velocity from both sides. We get v minus v0 equals to at. We can see this expression here in both equations, so we can substitute it in. Oh, actually, this part. We substitute at into v minus v0 in the second equation, so the displacement will equal to 1/2 times at times t plus the initial velocity times t. And if we multiply it together, we get our final equation. The displacement equals to 1/2 at squared plus initial velocity times time. It's exactly what I wrote here. It's the second equation. Now, for the third equation, it's a little bit complicated because it's a combination of the two we just talked about. We can derive the third equation by first writing out our first two equations, which are the final velocity equals to v0 plus at, and the displacement equals to 1/2 acceleration time squared plus the initial velocity times time. If we grab our first equation here and then rearrange it again, it would become v minus v0 equals to at. And if we grab our second equation, we can kind of do it backwards, meaning that we write it as changing x, the changing position, equals to 1/2 at times t plus initial velocity times t. Now we see acceleration times time in both equations, so we substitute this back into the second equation. We get the changing position equals to 1/2 changing velocity times time plus the initial velocity times time. To make it more convenient, we can multiply each term by 2. So we can get 2 times the displacement equals to the changing velocity times t plus 2 times the initial velocity of t. Okay, if we factor out the t, we can see t in both terms here. We get 2 displacement equals to, we factor out the t, v minus v0 plus 2 times the initial velocity. So if we get rid of the parenthesis inside, we know that it equals to t times v plus v0, right? Because in here it's just v minus v0 plus 2v0. And now we need to use the first equation again, the rearranged version of the first equation. We need to isolate the t here by dividing both sides by acceleration. So as we can get t equals to final velocity minus initial velocity over acceleration. We substitute this t with the equation over here. So what we get is 2 times displacement equals to v minus v0 times v plus v0 over acceleration. All right, now is the time to make your algebra teacher proud. What is a plus b times a minus b? It's a squared minus b squared, right? So in this case, we know that 2 times displacement would equals to v squared minus the initial velocity squared over acceleration. And if we times both sides by acceleration, we can get 2a delta x equals to v squared minus v0 squared. And we can just rearrange a bit. And we get our final equation. V squared equals to v0 squared plus 2a delta x. So you might ask, it's pretty complicated, right? Why would we need this equation? Well, we can see the third equation is the only equation that's without time. So when you're solving a kinematic problem and you see you're not given the time, you can use the third equation. Same for the second equation. You can see the second equation is the only equation without v. This one is without t. So if you are given the question without t, you use the third equation. If you're given the question without final velocity, you can use the second equation. But I'd say don't try to memorize every derivation and don't try to memorize each equation. You need to know how they work and you need to know when to use what equation. But in the actual test, the equation sheet will be provided, and you just need to be able to use it flexibly. I'd recommend when you see any kinematic problem, make a given list, see what are you trying to find and what information you're lack of. All right, that's all for today. See you next time.